Okay, so when you do the expansion, you should get that. And order of operations says you've got to do these first. And once you do those, then it should be fairly easy to see that these right here are going to add up to 0. So they'll drop out. And what you wind up with is a squared minus b squared. If you now think of it in terms of complex numbers, what happens here is that this becomes bi, this becomes bi, this becomes bi, this becomes bi, and this becomes bi squared. I is the square root of -1. So obviously, if you square it, you're going to wind up with the sum of the squares. These two right here are called conjugates. When you have a complex number with an a and a b, and you're adding them, the conjugate is the a and the b subtracting them. These two are conjugates. And when you multiply the conjugates together, you lose the imaginary part, and you wind up with a real number. So if we look at this from the standpoint of an example, I don't have to go through all the motions here. This is going to become 49 plus 9, and that's going to equal 58.
So what made it plus instead of minus?
Well, at this step here, this I squared becomes -1.
Oh, I see. So then you, oh, okay.
All right, I want to talk about something else here. Let's do an example of where we are converting a complex number from one form to the other, because I didn't get to do that last time. This is a complex number, and complex numbers are frequently represented by z for no particular reason, in the same way that integers are frequently represented by n. But take a look. If I have this complex number and I represent it here as a point, and I want to represent it in polar coordinates, it means the coordinates of this on the xy plane are -5, 7i. And if you remember, the x coordinate here, x is equal to r cosine theta. That's what this is. And this part right here, up and down, is r times I times sine theta. Y is just sine theta, but since this is the imaginary axis, you got to throw the I in there. So z is going to equal r cosine theta plus ri sine theta. That's because ri sine theta, that's this part right here. So r sine theta is the y coordinate. And so essentially this is the x coordinate, this is the y coordinate. Well, it's the a and b coordinates, but it's the horizontal coordinate because it's the real number. And +7 is the b coordinate because it's the number that's multiplied by I. It's the coefficient of the imaginary term. Here's what we do, just by the way. We factor out the r. And then in order to simplify the writing of it, we actually turn it into this, r cis theta. The c stands for cosine. The I is the imaginary number times sine, which is sine. So this is cosine plus I sine theta. These two mean the same thing. So when you're thinking to yourself, wait a minute, where's the I go? Well, it's still in there. It's right in the middle there. Let's go through this for a minute. Okay. If we want to get R out of this, we're going to have to take the Pythagorean theorem and use it to find the hypotenuse of this triangle. That makes this -5 squared plus 7 squared, and then take the square root. Okay. And that makes it square root of 25 plus 49, which in turn makes that square root of 74. when I want to get theta, I'm going to take the arctangent of this value over this value, right? 7 over -5. And what I wound up with was arctangent of -7 over 5 was -54.5 degrees plus 180n. Now, if you think about it, -54.5 degrees is way down here somewhere. And that's not the one we want, because the point we have is way up here. So we have to add 180 degrees to it. Okay, so we're going to wind up with theta being equal to 125.5 degrees. And when we put this all together, it means this z up here is equal to this down here. This is the rectangular form, and this is the polar form.
Wait, can you go back? Where'd you get -54.5 from?
If you put inverse tangent of -7 over 5, you should get -54.5. This is the thing where if you use your calculator to get this, you'll get -54.5. That's not the answer you need, though, because that's way down here. So instead, what you have to do is add 180 degrees, because the tangent of this angle here is the same as the tangent of the continuation of that line down this way.
For the bottom, the 74 cis 125.5, is the radical only over 74?
Yes.
Okay.
That's the R value.
So in the original equation, well, or I mean, when we're solving for R, are we treating the -5 and the 7 as x and y?
Yeah, we're treating them as the lengths of the sides of the triangle. This triangle right here. So this is 5 and this is 7 in terms of lengths, and this is going to be c, the hypotenuse, so it's going to be the square root of this squared plus this squared. Or if you remember, that's also the distance formula. The distance from here to here is equal to the square root of this distance squared plus this distance squared.
So to convert the imaginary equation that we had on top to polar, we just use the formula from, like, as if we were converting the coordinates, and then just use -5 and 7.
Exactly. Now, the thing to remember, okay, is that this is not the same as just converting the coordinates. The process is the same. But what you have to remember is that here, this is a number. This point on the complex plane doesn't just represent a pair of coordinates. It represents a complex number. So if you're asked to turn this, which is a complex number in rectangular form, into a complex number in polar form, this is the right answer. The mistake that is most often made in the classes that I've taught is this right here. This would not be the right answer to this question. These are the polar coordinates of a point, and these are the rectangular coordinates of the same point. These right here represent a complex number in rectangular form, and this represents the same number in polar form. So let's say we were going to do some arithmetic, and this is sort of why it's important to remember that z usually represents a complex number. Let's say I'm going to have two complex numbers. I'm going to call this one z1, and I call this one z2. Okay, so now I have two complex numbers in rectangular form, and I'm going to ask that we add them together. And as you can see, it's really a trivial task, because we're going to add these two things together. We're going to use the associative and commutative property essentially to add like terms. We're going to add the real numbers together and get -9, and we're going to add the imaginary numbers together and get 15i. Pretty straightforward. It gets a little more complicated when you start to do other kinds of arithmetic. If you look at page 617 in your book, you'll see that there are two things here and here that talk about other kinds of arithmetic you might wind up doing with complex numbers that are easier in polar form than they are in rectangular form. So for example, here, well, let's start down here. The reciprocal of a complex number in polar form, instead of taking 1 over a plus bi and trying to turn that into something usable, what we have instead is simply take the reciprocal of the modulus, that's the r value, and the additive inverse of the argument, which is the thing inside the parentheses of a function. And additive inverse means if it's plus, you turn it into negative, and if it's negative, you turn it into plus. So for a reciprocal, to get a reciprocal of a complex number in polar form, take the reciprocal of the modulus and the additive inverse of the argument. You'll notice there's sort of a pattern forming here. If I want to multiply two complex numbers in polar form, I'm going to multiply the two moduli, the two r values, and then I'm going to add the two values in the argument. So
Wait, can you say that one more time?
I sure can. We're going to multiply the moduli together. That's the r values. And we're going to add the values of the two arguments together. We're going to multiply the r values and use that for our new r. And we're going to add the two theta values and use that as our new theta. This is page 617 in your book. And if you turn the page in your book, you'll see that the quotient of two complex numbers in polar form is pretty much the same thing, except that instead of multiplying the moduli and adding the arguments, we're going to divide the moduli and subtract the arguments, which is not really all that surprising when you remember that dividing is the same as multiplying by the reciprocal, and the reciprocal involves using the reciprocal of the modulus and the additive inverse of the argument. Just like for multiplying, we're going to multiply the modulus and add the arguments. For division, we're going to divide the moduli and subtract the arguments. What becomes more interesting is the thing called de Moivre's theory. And that's on the top of page 619. And he's the guy who said, you know what we can do? We could actually use what we now know to find powers of a complex number. And if you think about trying to find the power of a complex number that's in rectangular form, you'll realize how really awful an experience that might be. Okay, so if we were down over here, right? Let's say we wanted to take this and find, I don't know, the 15th power of this. How many times are you going to multiply this over and over again, right? However, what de Moivre said was, if we want to take a power of a complex number in polar form, then what we do is we take the power of the modulus and multiply the argument by the value of the power. What does that mean? It means that I'm going to square the modulus, and I'm going to multiply the argument by 2. So this squared is this. And if I wanted to square it in this form here, I would have to say it's -5 squared plus 2 times -5 times 7i plus 7i squared, right? Because that's what happens when you square a binomial. And then you'd have to work all of that out. This is a lot easier. So those are a handful of arithmetic rules in polar forms of complex numbers that make life a lot easier. But wait, there's more. take a look at this and ask yourself, well, if that's what I wanted to do, how would I find the square root of this? Or the cube root of this? Okay, now we're talking about something that is virtually impossible in rectangular form, but not all that hard in polar form, right? Oh, by the way, one thing to mention here is that when we're writing out cis, the theta should be between 0 and 360. Should be greater than or equal to 0 and less than 360. It should be greater than or equal to 0 and less than 2 pi.
Wait, sorry, how'd you get 74 alone again and the 74 cis
Here?
251? Yeah.
Right. The rule on this is I'm going to, if I want to square this whole number here, I'm going to square the modulus, right? And the square of square root of 74 is 74. And I'm going to multiply the argument by 2.
So then if it was cubed, we'd do the cube of square root of 74.
Right. So
Multiply
this
by
would be
3.
this would be 74 times the square root of 74 cis 376.5.
Okay.
Okay, and coming into this, 376.5 would not be the right answer because it's bigger than 360. So I would have to call it 16.5 degrees. So let's look at this, right? What if I wanted to take the cube root, and I'm going to do a simpler number here. Right? I want to take the cube root of 8 cis 60 degrees. The key to this is to remember that taking the cube root is the same as raising it to the 1/3 power. Here, we have to do something a little bit different. And that's because we need to remember that although in standard form here, we're going to write this with theta between 0 and 360 or between 0 and 2 pi, the fact is that no matter how many times you go around and around the circle, there are basically an infinite number of ways that you can name one of these complex numbers. So that means that in order to do this 1/3 power, we're going to have to keep in mind that this is really 8 cis 60 degrees plus 360 degrees n. And it's important to remember that because it turns out that you get a bit of a surprise as your answer. Remember, what you have to do here is you have to take the power of the modulus. So it's 8 to the 1/3 power. And then you have to multiply the argument by the power. And the power is 1/3. So, and we're multiplying 60 degrees plus 360 degrees n. And that turns out to be this, 2 cis 20 degrees plus 120 degrees n.
Wait, the only question I don't understand is how did you get make it that so that 1/3 was multiplied by what was in the parentheses instead of taking to the power anymore?
Well, that is what Demoivre's theorem is on page 619. The theorem says that if you're going to raise a complex number in polar coordinates to a power, the way you do that is by raising the modulus to the power and multiplying the argument by the power.
Thank you.
Mm-hmm.
Wait, so why did we add the 360n again?
Well, let's say this is the complex plane, and let's say we have a point here. I can call this r cis theta, but the truth is, it's also r cis theta plus 360 degrees. And it's also r cis theta plus 720 degrees. So there's an infinite number of ways to do this. The reason you have to think of them this way is because when I divide theta by 3, I'm going to get this over here. When I divide theta plus 360, I'm actually still going to get a number that's in the first circle. And when I divide 720 by theta, I'm going to get another value over here that's different from the first two. So what happens here, when I divide this out, I get 20 degrees, right? 2 cis 20 is one of my answers. But the next answer is still going to be within 0 to 360. So what's going to happen here is I'm going to have, what happens if n is equal to 0? It's 2 cis 20. If it's equal to 1, it's 2 cis 140. If it's equal to 2, it's 2 cis 260. And if I go around one more time, it becomes 2 cis 380. And that's past the 360 mark, which is what we're doing up here, right? It means that I've already counted that number once. So these are 3 different answers that work as the cube root of this original number up here.
What did you add to 20 to get to 140? And then 140 to 260?
2 cis 20 degrees is what happens if I don't go around a second time, right?
Oh,
if
okay,
I just go
that
to
makes
that
sense.
angle. If I go one more time, right? If I let this equal 1, then it's 20 degrees plus 120. If I let this equal 2, then it's 20 degrees plus 240.
Okay, thank you.
Sure.
So whenever we're doing this, we always have to say plus 360.
Yeah, because if you don't, you'll miss some of the answers.
So then why didn't we do it on the one above?
You mean on the earlier ones?
The
mean
one
over here?
74 cis 251.
Yeah. You're asking the right question. The right question is, why do I have to do it here and I've never had to do it before? And the answer is, in theory, we should do it everywhere. But here, it's not going to make any difference. Because if you do plus 360 and then you multiply the theta plus 360, it's going to be a multiple of 360, which means you're just talking about complete rotations. You're not talking about a fraction of a rotation. So let's say I even did leave it in and my answer became cis 251 plus 720n. So what happens if n is 0? I get 251. What happens if n is 1? Now I'm going to get 971. Well, what is that? Because I can't write it that way. When I put it into this form, the standard form, it's going to turn out to be 251 anyway, because 720 degrees is 2 full rotations.
So when would we do the plus 360n?
You have to do this whenever you're raising something to a power that's not an integer. Because remember, if I were raising z, a complex number z, to the 4/3 power, that's the same as taking the cube root of z to the 4th power. That's how this works. Have you guys done this before?
Yeah, I did this last year, I think, too.
Okay, so this should be familiar to you. What happens here is you're going to use this property up here, this theorem right here, twice. You're going to use it once to get the 4th power of z, and then whatever answer that you get for that, you're going to take the 3rd root. So anytime you have a number that's not an integer, the denominator is the root that you're taking. And every time you take a root, in order to get the right answer, you're going to have to use 360 degrees times n.
So the thing that we just did above that was converting the rectangular complex equation to polar.
You mean here?
Yeah.
There's no rectangular coordinates here at all. This is taking a complex number in polar form and raising it to a power.
Okay.
In this situation, we raised it to a power that's an integer, and it was pretty straightforward. We raised the modulus to a power and multiplied the argument by that power. When it came to a power that was not an integer, a rational power, then we had to use the denominator, which is essentially taking the root of a number, and use the same principle, which is I'm going to raise r, the modulus, by the power, and I'm going to multiply the argument by the power. But since the power is fractional, what I need to do is remember that this is 60 degrees plus 360 degrees n, because 60 degrees is coterminal. You're going to get the same thing every time you spin around 360 degrees. When you do that and you multiply the argument by 1/3, you get some number here plus some number here times n that's less than 360 degrees, which means every time you add this, you're moving some amount that's less than 360 degrees, so you're getting yet another answer to the problem until you get all the way around to the end of the first cycle.
So you said if it's not an integer, we have to do the plus 360. So if we have an integer, do we still have to do the plus 360?
No, that's what we were talking about up here.
Okay.
When you had the integer here, you didn't have to worry about it because there was no dividing
Right.
going on. It was all just multiplying.
Okay, thank you.
One of the things I included in the materials in Schoology was a pacing plan for the entire semester so that we have some idea of where we're going and when we're going to get there. These are the things we've covered so far, right? Introduction to polar coordinates, polar equations, and complex numbers in polar form. Okay, and we are here on the 4th day. So we have a couple of days now to continue to go over this until the test on polar coordinates, which will be on February 1st. Okay. At least that's my plan for the moment. You know, there are some things in here that may change as we go along. Here, and this is the reason to show it to you, here are problems in the textbook that you could be doing to practice or to determine whether or not you need more practice. In every class and during office hours, you can always ask me to help you with these problems or to show you how they're done. The one thing you can't do is come in and say, would you do number 16 for me? Because if you do that, I'm going to turn around and ask you, well, why don't you show me what you did and how far you got? You know, if you actually tried and couldn't figure out where to begin, we'll discuss that. But at the very least, you should be able to look at these and know where to begin and be able to follow along with what we've been doing, because we've gone over enough of these.